This satellite foundational course for GOES-R will teach you what you need to know about the scanning of the advanced baseline imager on GOES-R. In addition, you'll learn about the improvements on ABI related to improved spatial, spectral, and temporal resolution, how parallax can affect what you see, what the better bit depth on ABI means, and how multiple satellites with different resolutions will view North America. The authors of and contributors to this training are listed. They all work at the University of Wisconsin-Madison Cooperative Institute for Meteorological Satellite Studies. Learning objectives for this module are listed on this screen. Take some time to read through them. Some of the radiation knowledge you will have learned about in other modules. There will be a 60-fold increase in the amount of data sent by the ABI compared to GOES 13 through 15. The ABI on GOES-R requires a full disk image 5 times faster than the imager on GOES 13 through GOES 15. Spatial resolution on the ABI compared to present GOES increases by a factor of 2 in both horizontal directions. And there are about 3 times more spectral bands on GOES-R. The cubes represent the data volumes from present GOES in dark orange and GOES-R in beige. The combination of increased resolution means a 60-fold increase in data. About a terabyte of data will flow daily from GOES-R. This chart shows the Mode 3 scanning strategy for GOES-R. This is likely the default scan mode. This time chart shows strips of 30-second intervals across the top, and sequential 30-second strips that start at the left-hand side. During the 15 minutes shown on this chart, 1 full disk image is scanned, 3 CONUS images are scanned, and 1 mesosector is scanned 30 times in 15 minutes. Alternatively, 2 different mesosectors can be scanned 15 times in these 15 minutes. Note that each CONUS image is acquired in only 48 seconds that are spread out over about 3 minutes. White space on this chart is instrument idle time. No radiation is being sensed. This is a time chart of the continuous full disk mode that is the highest data rate for GOES-R's ABI and results in a full disk every 5 minutes. This might be used if multiple high-impact weather and volcanic events are happening, say a volcano in Chile, strong hurricanes over the Atlantic and Pacific basins, and high-impact severe weather over the central U.S. The most likely default mode is Mode 3, however, where 1 full disk image is scanned, 3 CONUS sectors are scanned, and 30 30-second mesoscale sectors are scanned every 15 minutes. Those 2 mesoscale sectors could be split in 2 locations, so you'd get 2 separate views with 1-minute imagery during the 15 minutes. This shows spatial resolution. Pixel areas are approximate, as a function of color, and apologies to the color challenged in the audience. A spatial resolution of 1 square kilometer occurs at satellite nadir, the subsatellite point over the equator. Each color bin is rounded to the nearest square kilometer. For example, pixels of size exceeding 9.5 square kilometers and up are binned into the red area denoting pixel sizes exceeding 10 square kilometers. The first dark blue ring labeled 1 shows pixel areas from 1 to 1.49 square kilometers. The next, lighter blue, shows pixel sizes between 1.5 and 2.5 square kilometers, labeled 2, and so on. This shows the GOES West location with a proposed CONUS sector. 2 mesoscale image sectors are also shown. These are selectable and have 1,000 by 1,000 kilometer size at the subsatellite point. These mesoscale regions therefore have different sizes and shapes for different geographic locations, but they have the same size in the number of horizontal lines scanned and the number of vertical elements scanned. The meso over Kansas will also be shown in the next 2 slides. This is a similar figure, but with GOES-R in the central GOES test location with a CONUS sector indicated. 2 mesoscale image sectors are shown. Again, these all contain the same amount of data, but their shapes depend on where they are placed relative to nadir. Note that the shape of the 1,000 by 1,000 region over Kansas is different now, but it's still centered at the same point as on the previous slide and is the same nominal size. This is a figure with GOES-R in the GOES East location. The CONUS sectors indicated, and 2 mesoscale sectors are shown. The mesoscale sector centered in Kansas has the same 1,000 by 1,000 size as on the previous 2 slides, but its shape is different because this is in the goes east location. The ABI allows more bands, finer spatial resolution, faster refresh rates, and on-orbit calibration of all bands. This is a tabular representation of that data. What does on-orbit calibration mean for reflective bands? That means that goes east visible and goes west visible will look similar on goes R and S. That's unlike present-day goes 13 and goes 15. Visible imagery from those two satellites is noticeably different. This shows the 16 bands, their central wavelengths, the wavelength range, the resolution at the subsatellite point, and the band nickname. The reflective bands shown here generally have little utility at night. The exception is the 1.6 and 2.2 micron channels that can have a signal for fires and volcanoes at night. Band 2 on the ABI, the 0.64 micron, is close to the present visible image on goes 13 and goes 15, which is also about 0.64 microns. Note that bands 1, 3, and 5, the odd numbers, have 1 kilometer resolution. This shows the infrared bands on ABI. The number of infrared bands is increased by a factor of 2.5, from 4 on present-day GOES to 10 on ABI. The stars appear approximately where today's GOES imagery bands fall. Bands 7 and 16 have close matches on present-day GOES. The water vapor channel and window channels on ABI are similar but not exact matches to current GOES. Here's a graphical image of current-day GOES channels, all 5 of them. Visible, shortwave IR, water vapor, window channel, and carbon dioxide. Compare that to what's coming with the future GOES. In summary, a lot more data is set to flow from GOES-R. The visible and near-infrared channels are useful mostly only during the day, with some exceptions for the 2.2 and 1.6 micron channels. This chart shows reflectivity values for various surfaces. Reflectivity differences between channels means that what is evident in one band will not be quite so evident at another band. For example, snow is bright white in the visible, but is not very reflective at all at 1.6. Some sample uses for the channels are listed, but many more exist. The red line in this figure shows brightness temperatures computed at various wavelengths. The spectral response functions for the infrared channels on ABI are also shown, as well as the band numbers and the band nicknames. In some regions, around 10.5 microns for example, atmospheric absorption is small and the brightness temperature is around 288 Kelvin or 15 Celsius. That is to say, the satellite will detect mostly radiation that is emitted from the surface and escapes without being absorbed by the atmosphere directly to space. Therefore, the emitting temperature is the surface temperature. In the strong water vapor absorption region around 6.5 microns, in contrast, energy at that wavelength that leaves the surface is absorbed strongly by water vapor in the atmosphere and then re-emitted from a higher and colder region. At some point in the vertical, when water vapor no longer exists above the emitting region, the re-emitted energy will escape unabsorbed to space, but it will be from a far colder region. In addition to water vapor absorption by carbon dioxide, sulfur dioxide, and ozone is present in this absorption spectrum. The different bands have many different uses, as shown here. There are lots of other uses that aren't shown. Switching topics now. Parallax is a well-known misnavigation that happens when something, a cloud feature in the atmosphere for example, blocks the view of the surface. Parallax error can be computed as a rather complex geometric problem. It is related to how high a cloud is and how far that cloud is from the subsatellite point, with the effect increasing for higher and higher clouds and for points farther and farther from the subsatellite point on the equator. In clear conditions, satellite observations come from the surface pixel and are navigated to that point. All satellite navigation assumes clear skies. A cloud that develops between the pixel and the satellite, however, will mean that information from the surface is blocked. Instead, radiation will come from a region that is closer to the satellite, but that is nevertheless navigated to where the straight line emission from the Earth would have originated in a cloud-free atmosphere. Here's an example how the storm report shifts relative to storm structure in a native projection and in a parallax-corrected image. Parallax correction must use the infrared image because the correction is a function of height as derived from infrared temperatures. Those corrections are then applied to the higher spatial resolution visible imagery. This shows present GOES views and MODIS views. The MODIS view has been degraded to ABI resolution of convection over the southeastern United States. A parallax shift is obvious in places, over far northwest Georgia, for example. In addition, the better resolution of ABI allows for more distinct detection of transverse banding at cloud tops. Such banding is often seen in regions of turbulence. Pilot reports of turbulence are indicated on these figures. Let's talk now about bit depth. GOES-R will send many more bits of information. In general, Heritage GOES had 8 bits of information at each pixel, or 256 different values. GOES-R will send 11 to 14 bits depending on the band. That means higher precision in the measurements. AWIPs can display 11-bit enhancements, and your eye can discern differences between 8-bit and 11-bit enhancements. This is an 8-bit display. The next slide will show 11-bit imagery. The 11-bit presentation shows subtly smoother gradients. 8-bit presentations from the previous slide have been cut out and are displayed near their 11-bit counterparts. The importance of 1-minute data is well known. GOES-R will offer mesoscale sectors with 1-minute sampling so that better monitoring of cloud top features or fires, for example, are possible. There are examples available at the URLs listed. In addition, the figure insert shows brightness temperatures for the Buffalo, Oklahoma fire of 18 February 2016 at 1-minute increments. The red dots show how the fast-changing fire would be sampled at 5-minute increments. Many quick changes are missed by the 5-minute sampling frequency. This is what present-day information gives you. The temporal resolution is not sufficient to monitor quick convective development. In contrast, 1-minute scanning with future GOES, approximated here with GOES 14 SRSOR imagery, will allow better temporal resolution that better monitors quick convective development. GOES-R has better resolution in all ways than GOES 13, 14, or 15. Where does GOES-R supply better spatial resolution compared to operational Heritage GOES 13 or GOES 15? This color-shaded map shows approximate pixel sizes for GOES-R as GOES West. Included in the image is the CONUS projection to show the region scanned every 5 minutes. Note here how GOES 16, GOES West IR resolution that is 2 kilometers at nadir, that is at the subsatellite point on the equator, degrades to around 6 kilometers over the western Great Lakes. Here's the same image for GOES 13 as GOES East using the same color shading, and the CONUS image for GOES East is shown too. GOES 13 resolution degrades from 4 kilometers at the subsatellite point to around 6 kilometers over the western Great Lakes. So, if GOES-R is GOES West at 137 West, and GOES 13 remains GOES East at 75 West, the midpoint longitudinally is 106 West. But that's not where satellite resolution would be the same for each satellite. Instead, GOES-R would have better spatial resolution than GOES 13 all the way to 92 degrees west, the approximate longitude of Duluth, Minnesota, at the western tip of Lake Superior. If GOES-R were GOES East, superior spatial resolution from that GOES East relative to the resolution of GOES 14 or GOES 15 as GOES West, that superior resolution would extend west all the way to 120 West, the longitude of Reno, Nevada, and Santa Barbara, California. When GOES-R and GOES S both are operational as GOES East and GOES West, the poorest spatial resolution will be along the 106-degree west longitude line. Glasgow, Montana, and will therefore have the dubious distinction of the worst horizontal spatial resolution in CONUS, because it's halfway between the two satellites and it's farthest north. This image shows the 2 CONUS projections from GOES West and from GOES East. It stretches all the way from the Aleutians to the Eastern Caribbean, and from Hawaii up into the Canadian Maritimes. Here's a list of some acronyms used in this training. plus a link to go to for more information about GOES-R. This is a summary to remind you what you've just learned. This is the conclusion of the Satellite Foundational course for GOES-R on the basic operations of the ABI on GOES-R. Thank you for your attention.